topic of this conversation is a project that I've been working on for the past few months. It's this particular project that is real-time news clustering to understand news events as they're occurring. For that, let's go back in time a little bit. When I was at school, I was studying physics of MRI and employing spatiotemporal statistical noise reduction techniques to combine them with physiological modeling to understand blood volume in different parts of the brain. The dimensionality of the data that I was working at NYU was 256 pixels by 256 pixel in the XY plane. Along the z-axis, about 10 to 12 slices, and the temporal dimension was 6 minutes, about 360 seconds. So that's 10 to the power of 6. And we thought that's big data back then. We developed some nice models for that, and when I joined Chartbeat, I thought, oh, I could employ a lot of these models, statistical techniques, and I could help publishers understand their readers better. But I noticed that the scale of the data at Chartbeat renders all my models prohibitive, basically. And what I've been spending my time during the past year and a half is thinking about how to bring the computational CS, computational scalability to statistical techniques that focus on accuracy and performance of your model. Traditionally, in statistics, you have a cost function that you're trying to minimize. As the number of data grows, the size of the data is a source of simplicity. And as it grows, you can invoke asymptotic results, and the quality of your inference improves. In CS, I think the size of the data is a source of complexity, something that you have to tame with computation and hardware. And I've been thinking a lot about how I can blend these two techniques together, these approaches together. Sorry, I have to use my notes. So that's that. Let me give you a brief overview about Chartbeat. We work with a lot of publishers, as I say. We help them track their traffics on the website. And how it works is that each publisher puts our JavaScript code on their website. Then in the reader's browser, that code continually sends a stream of pings to us. And those pings, let's say if I used to go to Gawker's website back in the days, those pings are like image requests. And the data is URL encoded in them. And we receive those pings, we aggregate them, analyze them, and give publishers some information about the state of their website. And how many people are on there, what they're reading, where they're coming from. Think about an editor in your favorite daily newspaper. They have so many choices that they have to make during the day, from what content to promote on the website, where to put it, what to promote on Facebook, Twitter. And with this data, with what we do, we give them some context into how their readers are interacting with their content on the web. So it makes that decision-making process for them a bit easier. The scale of the data at peak per day basis is 1.5 billion page views per day. And it comes from 50,000 different publishers. A lot of them are non-English publishers. A lot of them are English publishers. 40 to 80,000 new English documents per day get published, and we track them. And this is the breakdown on an hourly basis as they come in. So weekends less, during the weekdays more publications as expected. And these are the documents that we will go about clustering them real time as they're happening, as we're scraping them. Okay, so how can we go about this? How can we group them as they're being published? A lot of people have been talking about it, thinking about it. Take Google, for example. As you see, each one of those is a group of like articles about the same news event. Twitter Moments has, Google does it completely algorithmically. Twitter, human-assisted algorithms, and each one of those again, is a collection of similar tweets about the same event. Facebook trending, they used to use human editors to curate these lists, but now they're just using keywords, named entities, to come up with the list of like Facebook posts about that same entity. But at the gist of it, it's you want to group things that are about the same thing and different from other things that are in different groups. How you go about it is you have to have a mathematical abstract way to represent your objects, articles in this sense. So you have to embed them in a feature space. What is that feature space? What are the features? You can weight your features differently. We'll talk about that. Some maybe contribute more to the separation of the clusters, some contribute less. And the gist of every clustering, classification, dimensionality reduction is you have to have a way to measure a distance between two objects. So how do you measure that distance? As for the computational challenges, as I told you, size of the data is huge, and the real-time nature of it adds a lot of computational complexity. We'll talk about all of them. It's not that these are two separate categories of problems. The computational restrictions bear on the statistical approaches that you can use. Likewise, it's like a trade-off between your cost function, the accuracy of your algorithm, and the runtime and complexity of the algorithm. So you have to see where in that trade-off you want to be. And let's go on. OK. So let's say you find a way to embed your articles in some feature space. You can use words. I'll talk about this in detail later. But let's say for now, you can use all the words in a document. Each word will be a dimension in your feature space. And the weights of these feature dimensions dictate where your articles lie in that space. Let's say we've done that. Then we can go about clustering them. The textbook clustering algorithm. You have endpoints in a p-dimensional feature space. You want to come up with k clusters, and each cluster, cluster k, has, let's say, nk documents in it, or objects in it. The cost function that you're minimizing in that situation is the within cluster sum of distances. So given that you want to partition everything into k clusters, you want to come up with the partition that minimizes the within cluster sum of distances. First of all, you have to calculate the pairwise distances between any 2 points. And that's the order of pn squared. It's not exponential, so it's not that bad. But still, it's expensive. For real-time applications, it's expensive. Then you have to come up with all these different partitioning of your points and find the best one that minimizes that cost function. The number of those partitions grows with k and n, just to make it tangible. If you have 25 points, you want to cluster them into 4 clusters. That's going to be about 5 to the 10 to the power of 13 clusters. I just, off the top of my mind. No. So it's so expensive. I mean, you can do that even in the batch setting here, let alone real-time clustering. You have to solve it via approximations, and you have to be content with that suboptimal solution, solve it iteratively, like in k-means and all the clustering algorithms. For real-time application, the problems, as we talked about, that's for batch setting, not real-time. In the real-time case scenario, you have new documents coming in. Do you have to calculate the pairwise distance of the new documents with all the documents that you've already clustered so far? It's so many documents. Like, how far back in time do you go? It's going to be huge. 80,000 documents a day, and if you want to consider the last week, it's going to be about 500,000, 2 weeks, 1 million documents you have, and they keep coming in. So adds to the computational complexity. And another thing for this particular application, news, real-time news clustering, like the whole rationale is that you want to be able to pick up new news events as they're happening. So that means the number of your clusters is increasing with time. So you can come up with an approximation of the algorithm that I just talked about. First off, you don't have to compute the pairwise distances of a new point with all the points that are in your previous clusters. Let's represent each cluster with one central point, and that is M for cluster K. And when you have a new document, just calculate the pairwise distances with that center, cluster center. And let's say you have to allow creation of new clusters, right? Let's say if the distance of my new document to the closest cluster is higher than a certain threshold that you have to tune, depending on the granularity of the clusters that you want. So if the distance from the closest cluster center is higher than a certain threshold, this new document becomes the first element, the first article in a new news cluster. If not, you join it to the closest cluster center. So good, we made some improvements. Now, in calculating the pairwise distances, we reduced that from pn squared to pk. But still, as I said, this k, the number of clusters growing with time, and your lookup time will keep growing and growing. So let's assume that we've implemented the clustering, and we're detecting new clusters as they're appearing in time. This is number in an hourly basis. As you see, this is how news stories are. They grow with time. How can we solve that problem? One way of doing that is just, again, the context of this problem gives us a solution. Think about news stories. They don't live long. Lifetime of news stories is limited. FBI email scandal with Clinton, that's going to live a long time. But there will be new developments through its lifetime, and those maybe deserve to have their own clusters. So this is, let's say, this is an algorithm that I've been playing with Chartbeat. And I take a bunch of clusters, and I look at them at day 6 since their inception, right? And I look back in time, and I say, OK, the total number of articles that were in each cluster, what fraction of them were added on day 1, day 2, day 3, day 4, and day 5. This will give me an idea of at what rate articles get added or people write about that story on a daily basis. And you see, usually maybe the average lifetime is around 2 to 3 to 4 days. And what this helps you, how this helps you is that you can say, OK, when I'm measuring the distance of my new document to my previous clusters, I'm just going to limit myself to story clusters of the last week, and that's it, or 6 days, or 5 days. OK, so you're somehow bounding k, the number of clusters in that pairwise distance calculations. But another issue, again, is that as a news cluster is evolving, it gradually changes. You want to be able to capture the gradual changes, not the macro changes that maybe those deserve another cluster. But you want to be able to capture the gradual changes. And how you would do that, you want your cluster center to reflect those incremental changes. You can't, when you're adding a new document to the cluster, you can pull all the previous documents in that cluster and find the cluster center again. Ideally, you would like to have a way to incrementally update your cluster center. Because you see, some of these clusters have a lot of pages in them. And again, lookup time is high, your memory limitations, all those things are considerations. So best solution is to incrementally update your clusters. Let's say you've added your nth new document, xn, to this cluster. You update your old cluster using a learning rate. That is, there should be subscript k over there. Yes, so you let this learning rate drop and decrease as new articles are being added to the cluster, with the rationale that you want the story cluster to solidify around that story, and you don't want to let it grow indefinitely. So this way, it helps with if a new document appeared that's similar to this, but not quite, and it deserves a new cluster, you won't, and for some reason, it goes into that cluster, you don't change the cluster center drastically change. You'll keep it in place. Okay, so these updates are important. Another issue is, again, the nature of the news, how we write about things. At some times, we've noticed that some story clusters, two different story clusters, articles about the same story start on different tracks. As an example, the Wiener FBI investigation into Wiener's emails was very different than FBI investigation into Clinton's emails. But at some point in time, they became very different to separate, very, very difficult to separate. And you couldn't, it wasn't easy to say, are those different clusters? Are they the same? Basically, you want to add this level of flexibility that if the cluster centers started moving close to each other, you have this option of merging them. Okay? That adds to the quality of your clustering. A lot of what I talked about so far was about computational considerations, slightly some about the quality of clustering, but we're going to get into the statistics of it that deal with accuracy of your clusters now. So as I said, first step to go about your clustering is to embed your documents, objects in a mathematical space. And the choice of these features determine the granularity of the clusters that you will have. Let's take that example, okay? And one way to define your features is you take all the tokens, with the exception of stop words and whatnot, you lemmotize them and, or yeah, whatnot. You can take all the tokens. You can get more detailed and just take named entities. That will give you a clustering that looks more like Facebook's result. More coarse clusters that doesn't capture the nuances around coverage of a named entity, the nuances around the coverage of Anthony Weiner's scandal or Clinton's scandal. If you want to get those nuances and you want your clusters to be more granular, maybe you should focus on nouns, or even better, on noun phrases that are parts of speech that accompany nouns. So it's adjective and noun and any other part of speech that comes attached with the noun. And I chose to use noun phrases and I break them into tokens because assume an article has Barack Obama and Barack, and each of these would give you 3 different dimensions in your feature space. There's so much redundancy. But if you break them into tokens, just get Barack and Obama, you've reduced that 3 to 2, but you're also preserving the synergies. So yes, you can focus on noun phrase tokens that will give you more granular clusters compared to named entities, and probably have less noise compared to when you're using all your tokens. That makes your feature selection step easier if you're using noun phrase tokens compared to all tokens. I mean, you can get more complicated depending on your particular application. You can use subject, verb, object combinations, or you can use neural network techniques, doc-to-vec, or average word-to-vec for an article, and that's how you would embed your documents in your space. But anyways, choice of feature space dictates the quality of your clusters, the granularity, and it's very important. I want to point out to this library that was developed by Burton, a colleague of mine at Chartbeat. It's a general NLP text processing and analysis library. It lets you scalably extract all these nouns, calculate the distances between documents, different distance metrics, and so many other options that you have. You should check it out. And we use that at Chartbeat. So another thing that influences the quality of your product at the end of the day, real-time news clustering. Again, you want to be able to pick up new events as they're happening. And as I said, we're using noun phrases with this rationale that a lot of the news events are about nouns. Issues are nouns, names of people, names of places, organizations, all nouns, right? And with nouns, you have this complexity that there will be new nouns that you don't have it in your vocabulary at the time that you build your feature space. But you want to definitely allow a flexible way, so that your feature space can grow. Like when the volcano happened in Iceland, do you remember what it was called? No? No, yes. Yes. So when it happened in Iceland, we probably didn't have that word in our vocabulary. So one way of doing that is that allow a larger feature space, higher dimensionality, which has a couple of thousand or tens of thousands of empty dimensions, and fill them up as new words are appearing or new features are appearing. So you can extend your vocabulary. OK. So I mean, for now, the dimensionality of our feature space is around 1,500,000. That's a lot. That's a lot. And so that's P. And when you're calculating the distance, pairwise distances and whatnot, those things scale with P. You want to have a way to select which features are more important for your clustering. Not all features contribute equally to the separation of your clusters, right? And again, news is about something new. It doesn't mean that the less frequently used features are the ones that you should discard and ignore. Actually, those are, chances are high, are the most important features that you want to keep. And usually in NLP, what people do is that they trim off two ends of the spectrum, the tokens that appear too frequently and the tokens that appear the least frequently, right? And that's not what we want to do. We want to have some smarter way of selecting these features. And just some numbers, just to give you an idea. So average unique noun phrase tokens per article is about 4. And I said the dimensionality of our feature space is 1,500,000. And average unique noun phrase tokens that are used daily is about 200,000. So it's a good case for feature selection, right? So we can get as complicated as we want. And one way of doing that is weight your features. So when you're calculating your pairwise distances, just put a higher weight on dimensions that contribute more to the separations of your clusters, as I said. And Wj is the weight that you put along dimension, feature dimension j. How you calculate that is that you measure the distance between clusters. As an approximation for that, you can use the cluster centers and measure the distances, take the averages along each feature dimensions, and see, and then you would soft threshold whatever you get. It's like sparse clustering. Any convex optimization problem that has some sparse penalization is going to have soft thresholding one way or another as its solution. So you soft threshold those AJs, and lambda is your tuning parameter that determines how sparse you want the number of selected features will be. Like if your lambda is too much, your weight vector will be more sparse. That means your algorithm determines, oh, there are less important features. If your lambda is higher, if your lambda is lower, your solution will be less sparse. So you're using more of your features in calculating the distances. Yes, basically, I mean, I'm adding more and more parameters to tune, but we'll talk about that. So that's how you get your feature weights. I haven't talked about like distance metrics that much. OK, let's talk about that. So when you're making that decision, you remember we had a threshold, we have a new document, and we have all those clusters. We have a threshold, and we say, if my new document is close enough to this cluster, put it in that cluster. If not, it becomes its own cluster. Now, when you're comparing different clusters with each other, and let's say that's a new article, and these are two different clusters, that represents the center of that cluster, that one the center of the other cluster. As you see, this cluster has a higher within cluster scatter, which is the average of distance of all the points from its center. That one is a tighter, much tighter cluster. As an example, I can tell you from experience that a lot of the political campaign, Hillary and Trump's coverage, are just so scattered brain, just all over the place. And 5 minutes, okay. So it's very difficult, but a particular issue, but particular set of news that are maybe talking about their attitudes towards NRA, that deserves to be a much tighter cluster. And somehow, if you have an article that's in between, that fits in the cluster scatter of your larger cluster, maybe it should go there. So you should somehow scale the difference, the distance with the cluster scatter. And so this circle represents that cluster scatter. It's uniform in all dimensions, but that's not actually the case. These clusters have shapes. As you see that within average, cluster scattered, that circle doesn't capture the shape of the cluster. So in this situation where the new document lies, more along the principal axis of the blue cluster compared to the green cluster, and probably it seems like that's a better choice. But if you look at the centroids, the cluster centers, that's farther, this is closer. And if you scale with this within cluster scatter, it's too much along this dimension. It shouldn't be that high. So you want to use something to scale the distances, and this something should capture cluster scale and shape at the same time. Basically, you want a higher distance along a dimension with higher variation to count less than a small distance along a dimension with lower variation. That's the effect that you want to capture. Cluster covariance, or just the covariance matrix of a bunch of points, is what can capture both cluster scale and shape at the same time. But how to estimate it, to come up with your sample covariance matrix here, we're in a dangerous regime. The average number of articles per cluster is about 10. The dimensionality of the feature space, order of millions, as I told you. And this renders estimating, coming up with a good sample covariance, not feasible. There has been a lot of research done in that area. People have had solutions, like you can assume your covariance matrix or the inverse of it has a particular structure. It's diagonal or low rank, or it's dense and sparse and low rank. And but they're good. A lot of them are good for when your data is dense, or they're computationally infeasible for real-time applications. What you can do, a simple way that I can come up with, is to just calculate that cluster variation in a direction that's relevant to your new document. I'm not saying this is the best solution. Whatever solution that people will come up with will include this intuition for sure, but this is a good intuitive way of going around the problem of estimating and coming up with your sample covariance matrix. But so yes, anyways, what you can do is that project each point along this relevant direction and get the variance of those. And that's what you will use to scale your distance from the new point and cluster centers. Okay, so let's say we did all of these things. And let's say we came up with our clusters. there's a lot of subjectivity that goes in there. Like how do you tune all your hyperparameters that you had? And I told you, like, your feature selection, your distance metric selection, all those things have bearings on the quality of clusterings and also the granularity. It's very difficult. If you take 4 people in this crowd and ask them to cluster stories about Hurricane Matthew, will this be the same hierarchy that you will come up with? And I doubt it. I don't know. A lot of you may disagree with what I have here, but when it's difficult for human mind to come up with a canonical way to cluster the news articles, we can't expect our algorithms to do that. You have to accept that a big part of the problem is subjective. At the end of the day, it has to look good in the eyes of who's using the product, the editors, and you can get bogged down in coming up with metrics or algorithms to estimate the hyperparameters automatically. But I think in doing that, you will lose part of the truth at the end of the day. And that is that internet content is the vomit of human consciousness. It's very difficult to cluster them, classify them, group them together in a coherent way, in an optimal way. And I think we must not expect more precision than what the subject matter permits from I don't know how many centuries ago still stands today. And with that, that's me. That's my Twitter. I don't put anything data science related on there, but I don't know if you want to check it, you can check it. And hopefully you have no questions. But no, please ask me if you have any questions.
Do you want to take a few questions here and then go to the office hours?
Sure.
If you just repeat the questions for the microphone so that everybody
Sure.
We can take a few questions before she goes down for office hours. She'll be just downstairs for a little bit. So if anyone has questions, raise your hand. I'll take the mic over to you.
Okay.
Can an article be part of multiple clusters, like more than one cluster?
What is that?
Can an article be part of more than one cluster?
Yes. So, I mean, you know, I just talked about it. So it's a fuzzy kind of logic that we're trying to get at. It's a fuzzy kind of wisdom that we're aiming for, right? And if you employ probabilistic approaches, that captures that effect that you want. An article can be part of different clusters in a probabilistic way. But you know, the scalability constraints become bigger in real-time fashions for this kind of applications. It's a step in the right direction, but we're not still there for us to be able to use it for the scale of the data that we're dealing with and at the rate at which they're coming in. Yeah. Yes.
I have a question regarding the lifetime of the cluster. How did you measure the lifetime of cluster? You show the...
Yes, the graph. Let's go back. So I had some clusters, a couple thousand of them, and I looked at them at day 6 from their inception. So I aligned, you know, their start time, all of them. Day 1, 2, 3, day 6. Each of them has, you know, some number of articles in them. Then I looked back in time, day 1. How many of, you know, the total number of articles on day 6 were added on the first day? How many on the second day? How many on the third day? I took the fraction with respect to, you know, how many articles were in each cluster. So I had a bar plot, and I looked at the median of those. And this shows you the median of those clusters. I was surprised when I saw this, because I would imagine that a lot of the articles, a lot of the clusters will get populated like at the first and second day, and they slowly drop in time. But that was not the case. Interesting. It probably has to do with cluster granularity, maybe. Maybe if I made them more specific, the clusters are more granular, I would see something like an exponential drop, but it's somewhere in the middle, the granularity. Maybe when a new news event happens and people are writing about it, it instigates more in-depth, investigation of the piece, and more pieces come in on the third or fourth day. I'm not sure, but that's a question. How to count the number of articles?
Maybe like some article is kind of indirect, which you might miss. You didn't count, maybe?
Maybe, and you mean if it wasn't clustered correctly? Or?
Right, cluster is, it's maybe like it belongs to other cluster, but its actual meaning is actually in this cluster, for example.
Yes, so I think this was based on 5,000 clusters, and I vetted, I don't know, a couple of hundred of them by eye to make sure all the articles that are in the clusters are about actually the same event. And it was okay. I had to discard some clusters that were like the political, coverage of the campaigns. They're not so tight. They're just all over the place. So I had to discard things like that. And I'm not showing you the bar plots here, so I'm cheating a little bit. For clusters like Hurricane Matthew, those are the clusters that keep living for a long time, and they were contributing to, the error bar on the positive side to be larger. But again, as I argued, maybe if a news story lasts that long, Hurricane Matthew, maybe you want a different cluster for when it's in the Caribbean, than when it hits Florida, than when it hits South Carolina, so